The vertical cavity surface emitting laser, VCSEL, is a photonic chip that supports our daily lives in a wide variety of fields, including global communications, healthcare, and security. The pioneer who conceived and laid the foundations for surface-emitting lasers is Dr. Kenichi Iga. It all began with a single flash of inspiration written on a notebook. VCSEL, the laser that laid the foundations of optoelectronics. (1940), born in Kure City, Hiroshima Prefecture. As a youth, spent his time absorbed in drawing pictures of insects, assembling crystal radio, and so on. 1956, enrolled in Hiroshima University High School, developed a determination to be true to himself and remain steadfast in his goals. 1959, entered the Tokyo Institute of Technology, now Institute of Science Tokyo. When it came time to select a graduate thesis, Mr. Iga joined the laboratory of Associate Professor Yasuharu Suematsu, who had begun research in the new field of optical communications. Under the tutelage of Professor Suematsu, Mr. Iga pursued research on ruby lasers as an undergraduate and optical communications as a graduate student. The semiconductor lasers at that time were made as so-called edge-emitting lasers. In this design, the semiconductor chips emitted laser light from the sides of the chips in the horizontal direction. In his research, independent of the current industrial development, Dr. Iga set three key requirements. Oscillation at a single wavelength to ensure stable communication quality. Manufacture as a single unit to enable mass production with an efficient manufacturing process. Wavelength reproducibility to generate stable laser light at a consistent wavelength. Dr. Iga's dream laser had to satisfy all three of these conditions. The night of March 22nd in 1977, deep in thought, Dr. Iga wrote one idea in his research notes. What if the optical chip's layers were made as thin as possible and laser was emitted not from the sides but upward? This idea overturned conventional thinking. Dr. Iga named it the vertical cavity surface emitting laser. Later, it began to be called VCSEL. In 1978, Dr. Iga and his students presented his idea of a surface-emitting laser to an academic conference for the first time. It garnered little attention and reaction was muted. 1979, the first successful oscillation of a surface-emitting laser was achieved by current injection. 1982, single wavelength oscillation was confirmed in a 10 micrometer cavity length. This test confirmed the physical principle is right and the key is technology. Dr. Iga was now confident he could succeed in building his dream laser. 1984, Dr. Iga was promoted as a professor at Institute of Science Tokyo. Accompanied by like-minded students and engineers and surrounded by a variety of equipment and devices, Dr. Iga had the conditions he needed at last. 1985, Dr. Iga's team succeeded in generating the first room temperature pulsed operation. 1988, a breakthrough occurred in Dr. Iga's search for his dream laser. Hitherto, lasers had to be cooled to generate stable emission. Now, working with Professor Fumio Koyama of Tokyo Institute of Technology and lab members, Dr. Iga succeeded in achieving continuous oscillation at room temperature. The achievement of continuous operation at room temperature was the turning point for practical application, as it enabled reliability in mass production. Dr. Iga also succeeded in arranging lasers in a 5x5 two-dimensional array. The era of parallel lasers had arrived. In 1992, Dr. Iga and his students tested the prototype for a wavelength-swept laser, which could continuously vary output wavelengths by using an external mirror to mechanically vary the cavity length. This prototype became the model for MEMS tuning. Dr. Iga had now solved the three issues he had laid out initially. The world's smallest dream laser, an environmentally friendly technology, was now a reality. Based on VCSEL, innovative technologies began emerging one after the other. Principles of VCSEL. When voltage is applied to a chip's light-emitting amplifying layer, electrons and holes are injected into the layer. When these electrons and holes are recombined, light is generated and further amplified. Mirrors on the top and bottom of the active layer repeatedly receive amplification of the light. When this amplification of the light between the mirrors exceeds its attenuation, phase-aligned monochrome light is rapidly strengthened. Part of this phase-aligned light leaks out from the mirrors. A characteristic of VCSEL is that each device can be only microns in thickness and diameter, enabling laser in a single color to be generated in parallel with just a tiny energy input. As Dr. Iga advanced joint research between industry and academia, the application of VCSEL spread rapidly in the industrial world. The technology was applied to a wide range of applications, including optical communications, sensing, and even fields Dr. Iga did not foresee. Examples include light sources for printing in laser printers, computer mice, optical communications. Over 90% of data centers use VCSEL in their optical cables. iPhone 10. VCSEL arrays are embedded for face recognition. OCT. VCSEL has transformed ophthalmic and dental examinations. VCSEL is rapidly advancing into devices that can be tuned for a wide range of applications. As an educator, Dr. Iga served as the 18th president of Tokyo Institute of Technology. Today, Dr. Iga travels the world promoting the adoption of VCSEL and nurturing future technologies. Since he was a student, Dr. Iga enjoyed playing the double bass. Today, he performs as a player in the Machida Philharmonic Orchestra. Dr. Iga is a chair of the Machida Philharmony Baroque Ensemble. He has published books that bring together the topics of music and physics. The world of handling waves, which also applies to VCSEL. The profound encounter between the science and technology that captivated Dr. Iga and music is suggestive of much. Among his many awards, Dr. Iga is recipient of the Asahi Award, the Franklin Institute's Bauer Award, and the IEEE Edison Medal. He has written over 450 academic papers and more than 10 books. I have spent my life conducting research in the field of engineering. What's most important is to have a spirit of curiosity. When you encounter a phenomenon, ask what it is? What are its principles? What is it based on? Along with that curiosity, have the initiative to pursue those questions. Always keep that in mind. And when you're young, study hard. Today's world changes constantly, with new ideas and new developments emerging one after another. I hope you will develop new ways of thinking to grapple with these many changes. AI is developing today in countless fields, including electronic sensing, biometric interfaces, and next-generation communications. VCSEL has great potential to serve as an indispensable piece of that future. Dr. Iga's accomplishments will continue to support the development of optoelectronics in a diverse array of fields.